Hey everyone, welcome to The Explainer. Today, we're diving into something absolutely fascinating, the invisible but incredibly powerful world of electrostatic interactions. We're going to explore the fundamental mathematical rules that dictate how particles push and pull on each other across space. It's kind of like this microscopic dance, and we're going to figure out exactly how the whole shebang works. Let's get right into it.
So here's our roadmap for today. We'll start with the basics of Coulomb's law, then compare electrostatics versus gravity. After that, we'll cover the rules and limitations, dive into the principle of superposition, find the equilibrium point, and finally, look at what happens with charges in motion.
All right, Section 1. Basics of Coulomb's law, the fundamental rule of charge interaction.
So what exactly is Coulomb's law? Well, at its core, it's basically the mathematical rule that lets us calculate the exact force two-point charges exert on each other. Now, you probably already know the golden rule, right? Opposite charges attract, and like charges repel. But what's absolutely crucial to understand here is that this force is highly directional. It's precise. It acts strictly along the straight, invisible line joining the centers of those two charges. Let's look at the formula. F equals K times Q1 times Q2, all divided by R squared. Basically, the force is directly proportional to the product of the two charges. But I really want you to pay attention to that K variable, the medium constant. You see, electrostatics cares deeply about its environment. For a vacuum or just normal air, K is a whopping 9 times 10 to the power of 9. That massive constant alone is a huge clue as to just how incredibly powerful the electrostatic force truly is.
And that brings us to the real kicker of Coulomb's law, the R squared and the denominator. This right here is the inverse square law. It means the force decays incredibly rapidly as you move the charges apart. Think about it. If you just double the distance between two charges, say from 1 meter to 2 meters, the force doesn't just cut in half. No way. It plummets to 1/4 of its original strength. Proximity is literally everything in electrostatics. You bring things slightly closer, boom, the force spikes. You move them slightly apart, the force drops off a cliff.
Moving on to Section 2. Electrostatics versus gravity. A battle of the cosmic forces. So, how do these two forces stack up against each other? The crucial difference here is twofold. First, gravity is kind of like a one-trick pony. It only attracts. Masses always pull each other together. But electrostatics, it's dual-natured. It can attract or repel, depending entirely on the signs of the charges. Secondly, remember that K constant we just talked about? Well, electrostatic force is totally dependent on the medium you're in. If you drop two charges in a pool of water versus a vacuum, the force changes completely. Gravity, on the other hand, operates with a universal constant. It simply doesn't care if you're in a vacuum, underwater, or buried deep inside a mountain. The gravitational pull remains exactly the same.
But guys, here is the most staggering difference. Just think about the number 10 to the power of 42. It's astronomically huge. If you measure the tiny gravitational pull between two electrons, and then you measure the electrostatic repulsion pushing them apart, the electrostatic force is 10 to the 42 times stronger. To put that into perspective, gravity is almost laughably weak on the subatomic scale. Electrostatics absolutely dominates down there.
Okay, let's hit Section 3, Rules and Limitations, knowing the boundaries of our physics toolbox. Like any good tool, Coulomb's law has some strict boundaries you've got to keep in mind. First off, it's valid only for point charges. You can't use it for massive, extended clouds of charge. Second, it works perfectly when both charges are sitting completely at rest, or, if just one of them is moving. But the absolute hard line you cannot cross, if both charges are in motion, Coulomb's law goes right out the window. It becomes completely invalid. Why? Because the system starts generating magnetic fields, and this simple little formula just can't handle all that extra complexity.
Which brings us to Section 4, Principle of Superposition. What happens when more charges crash the party?
Now, this is a highly logical question. If our formula is specifically designed to only calculate the interaction between two charges at a time, how on earth are we supposed to figure out the total net force on a single charge when it's caught up in a messy, crowded web of multiple neighboring charges?
Well, the answer is the principle of superposition. The net force on your target charge is literally just the exact vector sum of all the individual forces acting on it. It's actually a beautiful concept. The private interaction between, let's say, charge A and charge B is completely untouched and unaffected by charge C suddenly showing up. We just mathematically layer C's new force right on top of what's already there. Oh, and here's a great shortcut. If you have a perfectly symmetrical setup, like identical charges placed on the corners of a square, all those forces pull equally in all directions, canceling each other out to a net force of exactly 0 at the center.
All right, section 5, the equilibrium point, finding the perfect balance in a chaotic system. I want you to imagine you've got 2 fixed charges and you're holding a third charge in your hand. Your goal? Place it so it feels absolutely 0 net force. It's basically a physics puzzle. Your tactical placement relies entirely on the signs of those 2 fixed source charges. If the source charges are the exact same sign, you've got to place your third charge somewhere on the line directly in between them so the pushing and pulling from both sides cancels out. But, and this is a big but, if those 2 source charges have opposite signs, putting the third charge between them is a disaster. It means both forces will push it in the exact same direction. So, to get that net 0 force, you actually have to place the third charge outside the 2 source charges.
But exactly where? Outside or inside? Our source material uses a really fantastic analogy for this. Think of the larger magnitude charge as the rich charge. It's got immense power and influence over long distances. The smaller magnitude charge, that's the poor charge. Its influence is pretty weak. If you want your third charge to feel an equal pull from both sides, it absolutely cannot stand right in the middle. That rich charge would completely overpower it. Therefore, to achieve true equilibrium, that third charge must always be placed physically closer to the smaller charge. By moving it closer, the lack of charge magnitude is compensated for by the proximity. It allows the smaller charge to effectively rival the power of the larger one.
Now for our final section, section 6, charges in motion, disrupting the balance.
Try to really visualize this for a second. You've got a positive charge sitting dead center between 2 other identical positive charges. It's just hanging out in perfect, happy equilibrium. The net force is exactly 0. Now, what happens if we reach right in there and give that center charge a tiny slight nudge directly toward one of the outer charges?
Well, because we pushed it closer to one side, the repulsive force from that side drastically increases. Remember that inverse square law we talked about? That massive force violently shoves the charge back toward the center. But wait, it's moving fast now, so it actually overshoots the center, sliding closer to the other charge. And then, boom, that side's repulsion spikes, shoving it right back again. By giving it just one tiny nudge, we've totally disrupted the balance and trapped the charge in this continuous oscillating dance back and forth. In physics, this is famously known as simple harmonic motion, or SHM.
Now, because Coulomb's law is mathematically precise, this dynamic dance isn't random. It's entirely predictable. For simple harmonic motion to happen, the restoring force has to be directly proportional and perfectly opposite to the displacement. That's your F equals negative kx. And once that motion is established, we can actually calculate the exact time period of the oscillation. We just plug the mass of the charge and a specific constant, let's call it k prime, straight into the standard harmonic formula. These invisible forces completely dictate the exact rhythm of the dance.
Which leaves us with a truly fascinating perspective to walk away with today. We tend to think of the objects we interact with every single day as completely solid and still. But underneath it all, on a microscopic level, they're governed by these massive, invisible electrostatic forces. They are constantly seeking equilibrium, constantly executing these tiny harmonic dances whenever they get nudged. So think about it. How do these invisible, perfectly oscillating forces shape the very structure, stability, and solidity of the entire universe around us? It's definitely something to ponder the next time you assume an object is just sitting there doing nothing. Thanks so much for joining me on this explainer, and keep questioning the invisible world.